Hello, Astronomy. Welcome to our second video lecture for Unit 2. This will be the second of 3 videos for Unit 2. Okay, so in the previous video, we talked about, let's see, Aristotle, Ptolemy, Copernicus, and Galileo. We're kind of going through a sequence of astronomers that lead us to the modern view of the format of the solar system. So today we're going to go through 3 gentlemen, Brahe, Kepler, and Newton. So Tycho Brahe. So, we just finished with Galileo. Brahe is actually a little bit before Galileo, chronologically speaking. He doesn't come after Galileo. Brahe is largely in Denmark. He traveled a bit throughout his life, but most of what we're going to discuss today is when he is in Denmark. And he's a very, very colorful character. You read about his history some in the reading. So his father had died at the service of the king of Denmark. And so the king sort of bestowed riches upon Tycho Brahe. Brahe sort of becomes a royal or a court astronomer for the king of Denmark. And, Brahe is known for many things, one of which is decades of painstakingly accurate observational analysis of where things are in the sky. In a minute, we're going to see how he builds the first sort of modern observatory complex, which is in Copenhagen in Denmark. This is a sort of drawing of it. Parts of it were underground. You can visit it today. That's what it looks like today. So Brahe, he didn't have a telescope. So what he did that was so noteworthy was he built instruments used to measure distances using like arc seconds, measuring differences in area in the sky. You can see what these guys right here are doing that were painstakingly accurate. And he would observe the locations of things, again, for decades, of the planets, of stars. He especially, a couple of things of note, there was a very famous supernova. He's in like I think he dies in the very early 1600s, like I want to say 1604. So he's mainly doing his work in the 1500s. But there was a supernova that was very famous. It was seen throughout Europe. A supernova is when a star dies. And over a course of days, the star or weeks gets very, very bright in the sky, and then eventually disappears. And, teachings at the time were that the cosmos is fixed, that it doesn't change. And the fact that you have a star, appear very bright, then disappear shows that it does change. He also did lots with comets. So the leading idea as to what a comet was that it was like a local disturbance in the atmosphere. Now we know comets are objects that orbit the sun. They're sort of nicknamed dirty snowballs. They're these huge objects in space that can be miles across. That when they get close to the sun, some originate from out way past, actually all of them originate from out way past Pluto in a region called the Oort cloud. We'll get to that later. But as they get near the sun, part of the material of the comet starts to vaporize and forms like a halo around the comet, and the solar winds push a tail back. But what Brahe did was he was able to get records of comets in different parts of Europe at the same time. And he could see that the comet doesn't really change, like on a given night, what stars the comet is in doesn't really change from where you are in Europe, which goes to show that the comet is much, much further away than it would be if it were part of the atmosphere. So comets are very far away. He also, one of his claims to fame is he's one of the guys who realizes things like comets, things like the moon, things like the stars are much further away than we think that they are, particularly when compared to the moon. Comets are way further out than the moon. The stars are way further out than the moon is. He also, with comets, he was able to track comets, and he found that, like picture the orbit of Mars, and the orbit of Jupiter, and the orbit of Saturn. He was able to show that comets, their paths cross multiple orbits, which they do. That's not surprising to you, hopefully. But if that's the case, then the whole idea of nested spheres can't be a thing if comets like cross multiple orbits. And again, to do that, you had to prove the comets are much further away than the atmosphere or that the moon is. Brahe, again, his observatory in Denmark, he collects decades worth of painstakingly accurate observations, many of which, or really all of which, are going to be sort of inherited by Johannes Kepler, who is our next gentleman in sequence. And Kepler is going to take those records and run with them. A couple things about Brahe. So you see he kind of has a weird looking nose there. Earlier in his life, he had been in a duel over an argument with a gentleman over math. I think it was over who was the better mathematician or something like that. And he had an injury to his nose. So he wore like a silver nose plate. I guess here it's painted to look like flesh, but he had basically a silver nose. And he died of a burst bladder. I think after an evening of overindulgence with alcohol. I'm not quite sure how that leads to a burst bladder, but that sounds very, very painful. But yeah, he dies of a burst bladder, which that's a horrible way to go. But anyway, Brahe, with Galileo, you think telescope, right? Brahe didn't have a telescope, but his records were so accurate that people used them to describe orbital motions in the heavens. Okay, I just love this picture. I think this is just a really cool thing. And again, you can see parts of it are underground. When you visit it, you can see you kind of go underground. Anyway, that's Tycho Brahe. Okay, so skip ahead to Johannes Kepler. Johannes Kepler was a German, and when Brahe dies, there's a long story behind this, but basically Kepler is sort of like his successor. And Kepler, you can see he's holding this little like compass-looking thingy. Like that's a really when you have your portrait painted, make sure you're holding something cool like a compass in it. You must have held it very, very steady for a long time. Anyway, so Kepler has 3 laws of planetary motion, which we're going to go through in a minute. Kepler, sort of revolutionizes some of our views of how things move in orbits, and Kepler kind of puts the final pieces in place to explain how and why, not so much the why, but how things move in space. Kepler, most notably, is the guy that figures out that the orbits of planets are elliptical, that they are not circular. And he resisted it a lot because the whole ancient Greek idea of the circle being a perfect shape, he kind of stuck with that pretty religiously. And it took him a long time to prove to himself that he was thinking was correct, that the orbits were actually elliptical, because ellipses aren't perfect shapes like circles. But you know what? That's okay. So Kepler has 3 laws of planetary motion. The first law of the 3, this one's probably the most important for our purposes. So it's that planets move in elliptical orbits, not circular orbits. So an ellipse, going back to geometry, you see this word focus right here. Ellipses have 2 what are called foci, right? Like picture a very long ellipse with 2 foci that are far apart. As the foci come closer and closer together, an ellipse turns into a circle. So essentially, like the orbit of a planet could be circular if it's an ellipse with basically the 2 foci so close together, there's one focus. He discovers this and goes on to discover that the sun is not the center of anything. The sun is actually at one of the foci for a given planet's orbit. All right, so the sun isn't the center of the solar system, it's at one of the foci. And one of the things that Kepler had Brahe's data, he had Copernicus's data, and when you do gravity in physics, so the Earth's going around the sun because of the sun's gravity, right? Basically, the Earth is falling toward the sun in a curved, what we call orbit. So how quickly something moves in its orbit depends upon the gravity of the object, like the sun, but also how far away you are from it. And the only thing that would make sense for Brahe's very accurate observations were if the speed of the object can change, right? And if you look at this diagram, this diagram is showing a couple different things that I want to point out. But here I have the sun, here I have a planet, here Helion's when it's closest, at Helion's when it's furthest away. When an object is closer to the sun, it moves faster, right? When it's further away from the sun, it moves slower. This picture, this burgundy area and this burgundy area represent equal times. So if it took 3 months to go that distance, in 3 months, it only went that distance, right? So the object is going faster when it's closer to the sun. If the orbits are purely circular, then the object's orbital speed doesn't change because your distance from the sun doesn't change. But here you can see when you're closer to the sun, you move faster. And that was the final like nail in the coffin. That's not the final thing that Kepler needed to accept to understand and to explain theoretically the observations that Brahe had been recording for decades, right? So the first law, Kepler's first law, is, you can read it. It's the one that says the planets move around the sun in elliptical orbits, and the sun is this, not the center, it's one of the foci for an ellipse. Second law is sort of nicknamed the law of equal areas. And basically, in this diagram, if you do the math, the area of this burgundy diamond and this burgundy triangle, the areas are the same, and the times are the same. So the law says that, like picture the planet here, it sweeps this arc. The area made in that sweeping with the sun, if the times are the same, then the areas are the same. So if you went, I'm going to make up a number, 20,000 square kilometers, that's not nearly big enough. Let's say 20,000 square kilometers in a month, right? Here you went a month, you went slower, but you covered the same amount of area, all right? And again, the idea here is when you're closer, you cover more area, but you're also going faster, all right? That's Kepler's second law of planetary motion, or the law of equal areas. And again, the more highly elliptical your orbit is, obviously, you're going way faster when you're closer, way slower when you're further out. Comets have really, really, really elliptical orbits, which another example of Kepler's second law. So this shows all three laws. This is the first law. The orbits are elliptical. There's the sun. The second law, equal area in the same time. So the area of section S1 and section S2, the time is the same, so the area is the same. The third law, we're not going to get into much detail. This is more of a mathematical thing. The third law says that the period or the time that it takes for an orbit, the period squared is proportional to the average distance cubed. So the time squared is proportional to the length cubed. This one we're not going to get into that much detail about. Just appreciate, like, I mean, that's a very, it's a constant relationship of things that orbit the sun. The Kepler figured that out. It's just remarkable what he was able to do. Again, largely using Brahe's data, but he's the one that came to these three conclusions. So the Kepler's three laws of planetary motion: ellipses, equal areas, equal time, and then this deal with the period squared being proportional to the length cubed. Okay, so that's Johannes Kepler. All right, now skipping ahead to Isaac Newton. So Isaac Newton, he's the big boy. He's probably the most influential, most famous physicist of all time. You could maybe argue Einstein, but at least until Einstein, Newton is for sure number one. So Newton is in England. Newton is after all these guys. Newton's get more toward the 1700s. Newton, you can read a lot about him. He's an interesting fellow. He was accused of his teachers as being a daydreamer whose mind wandered, who couldn't focus on things. And what was happening was he was focusing on things in his head really, really, really intently, which made him seem absent-minded or like he was daydreaming in class. Newton, oh gosh, I mean, what does Newton not do? So obviously, the unit of force that we use in physics is the Newton. So, I mean, a couple things I just want to mention briefly that he does that we'll talk about more so in Unit 3. So Newton's the guy that figures out Roy G. Biv, that the colors of white light that you can separate them into Roy G. Biv. And when you put them together, that's white light. He develops a new kind of telescope, the telescope that Galileo built or refined was called a refracting telescope. Newton devised a telescope called a reflecting telescope, which we'll do this in Unit 3. Reflectors are really better. They can be much lighter in weight. They can be bigger. They're not that heavy. If you want to see deeper into the sky, reflectors are great. So let's get into this. So Newton, you can read it. He invented calculus to help explain things he needed to explain. So those of you that hate calculus, you can blame Newton. So I don't want to get into too many details on this slide, but Newton's law of universal gravitation. So, Kepler made these observations. Kepler has, his 3 laws. Galileo basically formulates this universal gravitation idea that explains Kepler's laws. Like, Kepler made the laws and they're correct, but the explanation of why the moon orbits the Earth, why the Earth orbits the sun, why Ganymede orbits Jupiter, like why do things orbit the way that they orbit? He explained in his law of universal gravitation, the idea of the apple hitting him on the head, like that probably didn't happen. But what he does is way more detailed than that. I'm going to read this to you, so just bear with me. So this basically says, every object in the universe attracts every other object with a force directed along the line of centers for the 2 objects that is proportional to the product of their masses and inversely proportional to the square of the separation between the 2 objects. So the idea here is, if you have mass, you exert a gravitational field. And this F sub G is the force of gravity, all right? This big G is a constant we're not going to worry about. So the M1 and M2 are the masses of the 2 objects, and the R is the radius or the distance between their center. So let's just say this is the moon and the Earth, all right? The force of gravity between the moon and the Earth is proportional to the mass of each object times themselves. So if the moon or the Earth gets bigger, if the M1 or M2 gets bigger, the force gets bigger. That's not shocking. Divided by the radius squared. So this is in the denominator. So as the objects get further away, especially if you square that distance, the force of gravity goes down. So if I want to increase the force of gravity between 2 objects, you can increase their mass, or you can decrease their distance, okay? So, you exert a gravitational force on the Earth, right? You do. Obviously, the Earth exerts gravity on you because you stay on the Earth. Well, the opposite's true too. The force of gravity between you and the Earth is proportional to the mass of you and the mass of the Earth multiplied, divided by the square of the radius of this between the center of the 2 objects. So obviously your mass is much less than the Earth's mass. So in terms of the relative effects of the force is the same between the force of the Earth on you on the Earth. It's exactly the same. But because you have less mass than the Earth, the sort of like the practical realization of the force is more on you than you are on the Earth. So this explains why you gravitationally attract to the Earth, and the Earth to you also. Why does the moon orbit the Earth? Well, same difference here. You have a force of gravity between the Earth and the moon. Why does the Earth orbit the sun? It's the same thing. This formula for universal, or equation for universal gravitation, works for anything. Why do comets orbit the sun? It's the same thing, all right? In terms of the moon, the moon's far enough away where it doesn't fall directly to the Earth. The moon falls around the Earth. So it's basically like the moon is falling at the same rate as the Earth is curved. So it's falling around the Earth, right? If you were to fall, a meter every second, but the floor goes down a meter every second, then you're falling with the floor moving. You're falling with the floor. So the moon orbits the Earth. The moon is falling with Earth's curvature, right? So when you're in space, people say, there's no gravity. Well, there is gravity. There's gravity in space. You're a little bit further away from the Earth's center, but not that much, right? But the gravity of Earth is pulling you toward the Earth, but you're falling with Earth's curvature. Okay, so Newton's the guy, and Newton figures out how to get things in space, how to get things to orbit way back in the 18th century. He figures out how you can orbit the Earth. course, he couldn't do it because they didn't have rocket technology that would get you going that fast. But he theorizes how to orbit the Earth, and he's right. Obviously, Newton is most famous for his 3 laws of motion. If you do this in middle school, if you're taking physics, you do it in physics. So the first law is the law of inertia. A body at rest will remain at rest, and a body in motion will remain in motion unless acted upon by an external force. So basically, in fewer words, an object's motion resists change. All right, motion resists change. So if you're moving, you want to keep moving. If you're not moving, you want to stay not moving. If you're moving, what would slow you down? Well, friction with the ground, air resistance, things. There are forces on Earth that would slow you down. But if you throw a ball in space, it's going to keep going forever unless another force acts upon it. The second law is the famous equation F equals ma. The force acting on an object is equal to the mass of that object times its acceleration. So F is force, m is mass, a is acceleration. If I want to know the force of an object, you multiply the mass of that object by any acceleration that the object has. So if I want to increase the force, you could increase the mass, which is not surprising, or you could increase the acceleration. So think of like a car crash, the force of a car crash. If the car is made of styrofoam, you're going to have less of a force because the mass is lower, right? If I have 2 cars of equal mass, but one car is accelerating faster, you're going to have a greater force, right? And then the third law is pretty famous. For every action, there is an equal and opposite reaction. This is obviously how rocket technology works. When you have a rocket, it's basically a controlled explosion where all the gases in the rocket are combusting, and they're looking for anywhere to get out. And of course, the rocket has the exhaust at the bottom, so the force of the rocket goes down, so the rocket goes up. Of course, if the force of a rocket finds another way out through a little crevice or a little weakness in the rocket, then the rocket turns into a bomb and it explodes. But yeah, that's Newton's third law of motion. Okay, so that's it for our second video. I hope that was helpful, and I will see you guys next time.